Welcome, everyone. I'm Councilmember Karen Farrer. It's a pleasure to be here, and thank you for joining us this evening for the first virtual Malibu Library Speaker Series. The Malibu Library Speaker Series is a program of LA County Library and the City of Malibu, featuring experts, authors, and notable figures discussing a wide range of subjects meant to appeal to a broad section of the community. Speakers discuss subjects including the entertainment industry, literature, science, the arts, education, sports, travel, food, and the environment. Tonight, we welcome Dr. Jessie Christiansen, an astrophysicist and research scientist working at the NASA Exoplanet Science Institute at the California Institute of Technology. She has published multiple exoplanet discoveries, the discovery of planets that exist outside of our solar system, and co-authored discoveries on thousands more. Dr. Christiansen will speak on Truth is Stranger Than Science Fiction. Now, please join me in welcoming Dr. Jessie Christiansen.
Hi, everybody. Thank you so much for having me tonight. I wish I could be there in person, but I'm really glad to be talking to you either way. And I'm excited to be talking to you about exoplanets. So these are planets around other stars. And in particular, what I want to talk about is the fact that we've actually been thinking about this idea of planets around other stars for a really long time. And we've made up all of these incredible stories and worlds and imaginations about what they might look like. And now that we're actually out there finding them, how much wilder nature even is than our imagination. So this is my presentation, Truth is Stranger Than Science Fiction. Okay, this is a classic sci-fi planet. I'll give you a few seconds to see if you can recognize it. Some Jeopardy music in here. This might help. Yes, this is the Enterprise, and this is Vulcan. This is the planet Vulcan. This is where the species Vulcan come from. This is Spock's homeworld. This is the planet Vulcan, also known as Vulcanus A2, Navasa 2, or 40 Eridani 2. Astronomers like to give everything lots of names. If you go outside and look up in the sky tonight, you will see stars that have dozens of names each. It's actually very confusing to keep track of, but that's part of what I do. Okay, so how did we get to Vulcan? Let's talk through a little bit of the history of the real search for planets and the fictional search for planets. So more than 2,000 years ago, 2,500 years ago, the Greek philosophers were discussing whether or not Earth, our Earth, was singular or plural. Were there many Earths, or was there truly only one individual Earth? And actually, Plato and Aristotle argued that the Earth was singular, that there was only one Earth. So we thought about it for a while. The Greek philosophers, very hypothetical, right? Like the same way we think about multiverses today is how they were thinking about this idea of other Earths. They had no way of finding them. It was all just a thought exercise. They like to sit around and think. So let's fast forward nearly 2,000 years. In 1300 AD, we have Dante's Paradise, this incredible, amazing story that Dante came up with. It's one of the first times that the planets of our solar system appear in fictional works. And so he explores this idea that, the planets are in concentric circles around the Earth, which was kind of the scientific view of how everything was arranged at the time. And he's going through the levels and describing the interesting things at each different planet. So this is, more than 700 years ago now, is when we first start to see planetary worlds appearing in works of fiction. Okay, fast forward another 200 years. Now we're in the Renaissance. So this is an amazing time for science and art and literature and math. And there's this Italian mathematician, Giordano Bruno, and he has this quote, which I'm going to share. There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. This is one of the first times in the modern scientific era we hear about this idea of exoplanets. And Giordano Bruno isn't just like speculating, is there or aren't there? He's straight up stating he thinks that there are countless Earths. So all the stars in the sky, they're just stars like our sun. Our sun is just another star. Our galaxy has 100 billion stars. So Giordano Bruno is like, you know what? All the rest of the stars, they're as good as our sun. They have planets too. So he's not even discussing it. He's just stating he believes that there are countless Earths. So Giordano Bruno was actually burned at the stake for saying this. He also said some other very silly stuff at a time when it was dangerous to say silly stuff about the Catholic Church. But one of the reasons he was taken in by the Inquisition and burned at the stake was claiming the plurality of worlds. So thankfully, these days, it's a lot safer to be a planet hunter, which is what I do. I'm not in any danger of being burned at the stake. But back then, this was a really bold statement to make, in no small part because the church believed, that God had made the earth and that was it. And so this was a bad thing to say when the church had a lot of power. Okay, so now we have this pretty firmly established idea in the world of science that there are probably planets around other stars. And I'll stress again, there's still no way for any of these people to test this idea. They were still finding planets in our solar system at that point, and telescopes were, just being invented and just being improved. So these were still just ideas. In the 1700s and 1800s, on the fictional side of things, we start to see a lot of science fiction and literature get set on the moon and then on Mars. So you might have, heard of the canals of Mars and this kind of thing. So we start to see lots and lots of stories really focused on the moon and Mars as places where stories might happen, where it's still human drama, but where drama might happen. It's very cool to see this evolution in science fiction of us taking our little human stories and putting them in other settings and seeing how that changes things. Okay, so now let's fast forward all the way to 70 years ago, 1952. So as I said, we've had lots of thoughts about exoplanets at this point, but no way of finding them. And this is where we start to get into the very cool technical stuff. Otto Struve was an astronomer, and he suggested this technique. So we knew that we could see stars going around each other. Lots of stars in the sky actually form in binary systems. There's two stars going around each other. And we had a way with spectrographs of measuring how fast the stars were moving. Now, Otto Struve was like, okay, what if you took one of those stars out and put a giant planet in instead, like Jupiter? You'd still be able to see the velocity change of this star as the planet's going around. Jupiter is actually pulling our sun around the middle of our solar system. So the sun is pulling on Jupiter, but Jupiter's pulling on the sun as well. And our sun is ascribing this little circle in the middle of our solar system with a period of about 12 years. That's the orbit of Jupiter as Jupiter goes around. So Otto Struve was like, okay, let's look at the stars around us and see if any of them are moving in the same way that indicates they could be being pulled by a planet. So he comes up with this idea. This is 1952. In the next 60 years, this paper gets 7 citations. Everyone thinks that this guy is crazy, in no small part because the only way his technique would work as he predicted it was if the Jupiter-sized planet was right next to the star, much, much closer, for instance, than Mercury is to our sun, so that it would only take maybe 2 or 3 days for the Jupiter to orbit its star. That's how close you'd need to be to have a measurable effect at the level Otto was talking about. And everyone was like, that's crazy because we know how planets form. You have to reproduce the solar system. So you have small rocky planets close to the star and then gas giants further away. Like we know that must be how it works because that's what our solar system looks like. So basically this idea was completely ignored by most of the scientific field. But there were a few people who were like, I bet I could build an instrument to test that. So we'll come back to those people. Then we start to see on the sci-fi side, fictional worlds. Now we're moving out of our solar system to exoplanets. We start to see exoplanets appear in science fiction in film and television. So in 1951, we have the movie When Worlds Collide, which has this properly fictional planet. It's not even just like one of our solar system planets. It's a made up planet. And in 1963, we start to see fictional exoplanets on television as well in Doctor Who. Obviously, he's from Gallifrey. He's from a completely different world. And we start to visit them in television as well. So now we're basically mainstream at this point. Exoplanets are on TV, but we still haven't found any. In 1995, only 25 years ago, the very first exoplanet was finally found after thousands of years at this point of thinking about this idea of could planets exist around other stars? Yes, they probably could. How could we find them? Here's maybe a way we could do it. Finally, we found the first planet orbiting an ordinary star like our sun, and it was found using the method that Otto Struve had suggested 40 years earlier. And it was this what we call a hot Jupiter. It was a Jupiter-sized planet that was orbiting its star every few days with a period of 2 days. So this Jupiter-sized planet is heated up to thousands of degrees because it's basically near the surface of the sun that it's orbiting. And since 1995, so this paper that Otto Struve wrote had about 7 citations in the first 40 years. Since then has had 100 citations because everyone's like, oh, he actually knew what he was talking about. And it also made us throw all of our planet formation theories in the bin because, as I said, we figured planets had to form the way they formed in our solar system. And now what we found is thousands of examples of planets that form in completely different ways. So let me walk you through some of the cool things that we found. So my job is I'm the project scientist of the NASA Exoplanet Archive. So NASA keeps track of all of the planets we found, where they are, what stars they are, what we know about them. So one of the things I do is I check the new planets that go in every week, and I was putting this one in. And remember how I said stars have lots of different names. So this is the star HD 26965. This is the default alias. That's the name that everyone calls it. HD 26965 rolls off the tongue. But it actually has appeared in many other catalogs. The 2MASS catalog, the BD catalog, the GJ catalog, all of these catalogs have this star in them. So you have to put on all these names and make sure they're all right. And one of them stuck out to me. It was 40 Eridani. And I was like, 40 Eridani? Why do I know 40 Eridani? And I'd love to be able to say I made the connection in my head, but I didn't. It just irked me. And I was like, I know this somehow. So I Googled it. And that is, of course, we're coming back to it. That is Vulcan. 40 Eridani is the system that the fictional planet where Spock is from orbits the star 40 Eridani. So here's the real 40 Eridani system. So it's a triple star system. So it's got a primary star A, we call the first star in the system A, and then there's 2 additional smaller stars B and C. So 40 Eridani A is the star that has the planet around it, just like in Star Trek, 40 Eridani A has the planet around it, Vulcan. So did we find Vulcan? Not really. What we found was a gas giant planet orbiting 40 Eridani A. It's much easier to find giant planets than small planets. For the same reason, if you go out into a grassy field, it's much easier to find the cow than it is to find a particular ant. Just so much easier to see the big planets. So we found a gas giant orbiting 40 Eridani A. But one of the things we have learned as we've discovered these thousands of exoplanets is that most stars have multiple planets. Like our sun has 8 planets. Most of the stars that we look at have planets, which is already just amazing to be able to say most of the stars in the sky have planets. And most of them have multiple planets. It's actually rare to find systems that just have one planet. So because we found a gas giant around 40 Eridani A, it's very likely that there are other planets around this system too. So we may have been honing in on Spock's homeworld, a rocky planet around this star. We're not there yet, but we're in the right system. This is Kepler 67, which is the planet that I could find in our archive. So we've got 4,500 planets that we found so far. The planet that we could find in our archive that was closest to Vulcan in terms of size, the type of star, and distance. So we haven't found Vulcan specifically yet, this fictional world, but we have found analogs. We have found rocky planets around similar kinds of stars. Okay. This was a really exciting thing for me. Obviously, I'm a huge sci-fi nerd and I love finding planets. So the fact that Vulcan could really exist really piqued my imagination. So what I did was I went through the Star Trek Memory Alpha wiki and found every single named planet that had appeared up until about 2 or 3 years ago. So this doesn't include Lower Decks and it doesn't include Picard. There were 938 named planets that had appeared across basically all of the Star Trek franchises up until that point. 51 of them, I could identify the real star that planet was orbiting. So that was a star that corresponded to a star that we really know about in real life. And some of the names were a little bit, I had to work with a bit, but there were 51 real stars that I could identify from these 938 planets. 7 of those 51 stars in real life really host planets. And so remember, Star Trek started in the 60s. Like this was well before we started finding planets in the 90s. So I just love the fact that, you know, sci-fi was able to predict not even just that planets are wild and varied and exist in many places, but also they were able to pick some real ones out. So seven known stars in our known real universe, where we are right now, have planets around them. One in particular that I enjoy is Tau Ceti. So Tau Ceti is a naked eye star. You can go outside and see it, probably not in Malibu, but generally you can go outside and see it. So this is the constellation Cetus, which is the whale. And this is Tau Ceti down here. And so this star we know in real life has 4 planets around it that we've found so far. And this is just an artist's impression of what those 4 planets look like. Almost everything I'm going to show you in this talk is artist's impression, because the actual data are very boring and hard to interpret if you're not a scientist. But this is what we're looking at. We're 4 planets. Now, the reason this is exciting is because in Star Trek, there are also 4 planets around Tau Ceti. So the fictional world had created this 4-planet system. And then in real life, we have discovered this 4-planet system around Tau Ceti. In real life, we're interested in this system because some of the planets might be habitable. So on the bottom here, I'm showing a little schematic of our solar system, not to scale. So this is our sun, and then you have Mercury, Venus, Earth, and Mars. This green shaded region shows you basically the distance range from the sun, where if you put Earth there, so you had an atmosphere and you had oceans, then you could keep the water on the surface liquid. Now, we could have a whole separate conversation about what you need for life. What are the necessary ingredients to look for life? But everything on Earth needs liquid water. So when we're going out and we're looking for other planets and we're trying to find potentially habitable planets, one of our criteria is liquid water. And that's already so constraining, right? Like if you just think about all of the science fiction I've talked about, there might be other solvents, there might be other liquids that you could form, long chain, interesting chemistry in that has chemical gradients that could lead to life. But right now we're talking about water. So Earth, actually, there's a little bit of wiggle room in our solar system, right? Like if Earth got a bit closer, you could still be habitable. If it got a bit further away, you could still be habitable. Now, Venus and Mars are obviously not habitable, but those are for reasons that aren't necessarily a distance from the sun. Venus has this huge, thick carbon dioxide atmosphere and has had a runaway greenhouse effect that has meant that the temperature on the surface is too high for liquid water. But that's to do with the thickness of the atmosphere, not so much the distance from the star. And then Mars is actually so small, it's only about 1/3 the size of Earth, that it wasn't able to retain enough of a thick atmosphere to keep the pressure at the surface high enough to keep liquid water. So that's the habitable zone. We call it the habitable zone. Another name for it is the Goldilocks zone, because it's not too hot and it's not too cold, it's just right. So if we go back to Tau Ceti and its 4 planets, we can see that the 4 planets, G, H, E, and F, we can talk about the naming scheme later, E and F are like right on the boundaries of what we would call the habitable zone. So they're a bit bigger than our planets. So you can see the size of the planets is to scale. So Mercury is quite small. Venus and Earth are actually about the same size. So these planets are all a bit bigger. And we don't know what the implications are for life there yet. Once you get like twice as big as the Earth, it might be that you have a very much bigger and thicker atmosphere. And again, that means strange things about pressure at the surface. So there might be life, but it wouldn't be Earth-like life. You couldn't take Earth-like life and put it on Tau Ceti E and F and have it be a nice, happy thing. You couldn't just like take your helmet off and breathe and be like, oh, well, I've landed. Unlike so many science fiction stories before. But Tau Ceti is this really cool system where not only did they get the star right, they even got the number of planets that we know so far right. It's pretty cool. Okay, we're going to jump franchises a little bit. We've talked about Star Trek. So Doctor Who, as I said, one of the very first times you see fictional worlds on television. And if you had a box that could take you anywhere in time and space, where would you go? This is a breakdown. I'm not going to label it yet. This is a breakdown of all of the places that Doctor Who has gone episode by episode. I'm going to let you think about it for a minute. A box that can go anywhere in time and space. Yes. Doctor Who spends most of their time on Earth. Not least of which because of the BBC budget, but also because that's where a lot of our interesting stories happen in our history. So you can go a lot of places in time on Earth and have interesting stories. The next largest place that the Doctor goes are Earth-like planets. That's basically, they're calling it something else, but it has a blue sky and it has plants and it has a breathable atmosphere. You can just step out of the TARDIS and you're fine. The next most common kind of planet that Doctor Who goes to is Earth-ish. Now that's where they've put like a red filter over the camera and they've like made the rocks be slightly different and interesting, but it's effectively still a surface that you walk on an atmosphere. There's probably liquid somewhere. Now I'm kind of doing this breakdown because science fiction did an amazing job of, coming up with all of these ideas of places we might go. But there are still ways in which science fiction is very constrained. Many stories still fall back on very anthropocentric needs and worlds, so Earth-like worlds. As I said before, one of the reasons we really love science fiction is because you take this human drama and you put it in this otherworldly setting, and you explore what that means. But it still requires taking the human drama and taking it somewhere else. So it needs to be able to support that human drama wherever it is. So there are still these limits that we put on sci-fi in many cases. And there are some truly imaginative authors who really break that mold. But, even in science fiction, we're stuck thinking about Earth. And science is actually reflecting that in the same way. So as I said, we're looking for liquid water. And that's because we know our kind of life needs liquid water. But what about the truly imaginative ideas where you don't need liquid water at all? It's a completely different type of life, a completely different kind of chemical energy gradient. It's just hard to get funding to look for those kinds of things because we don't have the necessary basis to say, we know that this could create life. So there's the same tension in science as there is in science fiction of like, how centered on Earth and Earth-like do you keep it so that it really connects to people and to funding agencies? So there are some episodes of Doctor Who where they do get off something even remotely Earth-like. There are some uninhabitable places they go to where they actually do need like the bubble of the TARDIS to keep them safe. Some episodes are just in space, which are frankly the ones I like the best. And some of them are really imaginative, like they go to a black hole or they go to an asteroid belt or they go to a disintegrating planet. Like those are really, we're properly getting away from some nice little safe bubble and exploring the galaxy. Those are also very, very cool. But most of the time, Doctor Who is on Earth or a planet very much like Earth. And I want to shout out to my colleague, JJ Eldridge, who was the one who actually went through and put all this data together. So thank you, JJ, for letting me use that. Okay. My favorite episode of Doctor Who is called Midnight. Midnight is a bottle episode where the Doctor is trapped on a shuttle on a crystalline planet. And the crystalline planet is called Midnight. That's why the episode's called Midnight. And, this planet is a tourist destination because of its amazing crystalline structures and the incredible, they call it X-ionizing radiation. So, you go for a spa and you get the special radiation. In real life, I wanted to talk about a planet called 55 Cancri E. And I'll stop and say, I'm really sorry about planet names. They're all terrible. They're all boring. I wish that they were more interesting. My job is to catalog them. Unfortunately, I don't get to decide the actual names in most cases. So 55 Cancri E is the fourth planet that was found around the star 55 Cancri, which is the 55th brightest star in the constellation Cancer. So that's how we get to 55 Cancri E. Anyway, so when we found this planet, it's a rocky planet right next to its star. Again, very, very short period orbit, very, very superheated. And one of the things we found about it is that it has an incredibly high carbon content. And what happens to carbon if you put it under incredible pressure, for instance, from tidal forces from the star nearby, just pulling on this thing, and temperature, it turns into diamond. So this has actually been called the diamond planet by a number of scientists now, because we think that the carbon is under such high temperature and pressure that there's basically a shell of diamond inside this planet. And so the headlines when this came out were all like, Tiffany's Eat Your Heart Out, biggest diamond in the galaxy. But this is a diamond planet. And it's, analogous to this crystalline planet that we had in Doctor Who of Midnight. So that's just another fun one. Gallifrey, so as I mentioned, Doctor Who's home world is Gallifrey. This is a still from the show. And what you see is there are 2 stars in the sky and at least 3 worlds. It's a little hard to tell whether this is a moon or these are both moons of this one, but there's at least 3 worlds. And one of the things, this is Kepler 47, that we've actually discovered is a very similar analogous system where we have 2 stars and 3 worlds. These are 3 separate planets. None of them are moons of the others, but there are 3 worlds here. So even like 1963, imagining this idea of Gallifrey, this truly strange otherworldly thing, we've actually been able to find almost exactly that, Kepler 47 with these 2 stars and these 3 worlds. So that's a lot of fun. So I threw a couple of Kepler names out there. So Kepler 67 earlier, Kepler 47 now. This is Kepler. Kepler is NASA's space exoplanet hunter that was launched in 2009 and lasted until 2018. So it's a 1-meter telescope that we launched into space that had the very specific goal and this is going to come back to this tension again with science fiction and sci-fi, the very specific goal of finding out how common planets like the Earth are. This is the Greek philosophers' questions from 2,000 years ago. How common are planets like the Earth? Now, Kepler didn't, in the end, it turns out, find any really Earth-like planets. And we'll talk a little bit about what makes something Earth-like. But it found enough things that were enough like Earth for us to feel pretty confident in saying, we think Earth-like planets are common. We actually think that almost every star in the galaxy has planets. And we think that 20 to 50% of the stars like our sun, so yellow, boring, middle-aged stars like our sun, 20 to 50% have planets like the Earth. So when I say planets like the Earth, what do I mean? So here in the top is our Earth orbiting our sun, not to scale. So in this schematic, I'll say that the stars are all to scale with each other in terms of size and color, and the planets are all to scale within themselves in terms of size, but the stars and the planets aren't to scale. So the Earth isn't actually bigger than the sun. The sun is much bigger than the Earth. So this is what we're looking for with Kepler. We're looking for Earth-like planets orbiting sun-like stars. And this is kind of what we found. We didn't find anything like Earth, just spoilers, unfortunately. So when we say like the Earth, what do we mean? There's 3 criteria that we had, that NASA had for Earth-like planets. One was a rocky planet. So in our solar system, we have the rocky planets, Mercury, Venus, Earth, and Mars. We have the ice giants, Neptune and Uranus, and we have the gas giants, Jupiter and Saturn. So NASA wanted rocky planets. I'm like, okay. The second thing was stars like the sun. So that, I'll get into that a little bit more later, but that was basically because we know that stars like the sun can support life because we're orbiting a star like the sun. So we were looking for planets around stars like the sun. There's actually many, many, many different kinds of stars in the galaxy, and our sun is not the most common kind. The third criteria was this temperature. So remember, I showed you that green Goldilocks zone, the habitable zone. So you need to be the right distance from the sun, from the star that you're orbiting, such that you could have liquid water on the surface if you had an atmosphere. So that's the third criteria, the distance from the star or the temperature of the planet, basically the same thing. So we never found anything that satisfied all 3 criteria, but let's walk through what we did find. So the first one is Kepler 20e. This was our first really rocky planet that we were satisfied. It was, the right size. We knew the size, we knew the mass. We were really excited about it. Unfortunately, this one is way too close to its star. It's orbiting, in less than a day. But that means, if you take a rock and heat it up to thousands of degrees, what happens? You get lava, you get molten rock. So we think that the surface of this planet, the side facing the star, is just molten. It's just a lava ocean, which means basically we found Mustafar, where Anakin and Obi-Wan had their big final dramatic fight. This is Kepler 22f. This is a water world. So it's about twice the size of Earth, which we think now is too big. Once you get to twice the size of the Earth, we think that you've probably got too much of an atmosphere and too much of an ocean, essentially. So when we looked at this one and we measured the size and the mass, it basically has the density of water. So it's probably not entirely water. It probably has like a rocky core and a deep ocean and some kind of atmosphere, but it's probably largely water, which means that we probably found Kevin Costner's water world, homeworld. The next one is Kepler 186f. Now, Kepler 186f, we got really close. So it's a rocky planet. So it's the right size for it to be rock. And it's the right temperature. It's the right distance from its star to have liquid water on the surface. The problem with Kepler 186f is its star. Remember how I said our sun isn't the most common kind of planet in the galaxy, most common kind of star in the galaxy. The most common kind of star in the galaxy are called M dwarfs or red dwarfs. They're much smaller and much cooler than our sun. And Kepler 186f orbits one of these M dwarfs. The reason that's a problem is that M dwarfs put out very different kinds of radiation than our sun. Life has basically evolved to be pretty good with the sun's radiation. There's a little bit too much UV, which is why we wear sunscreen when we go outside. There's a little bit too much X-rays. So occasionally when there are big solar flares, it messes with our communication equipment and stuff. But we're actually pretty okay with our sun's radiation. The reason our sun looks yellow is in the middle of the visible spectrum, which is where our eyes have developed. Chlorophyll and photosynthesis developed because of our sun's radiation. Life on Earth is pretty much geared towards the spectrum of our sun. M dwarfs put out a very different kind of radiation. And in particular, they put out much more of their energy as X-rays and UV, the things that I just said were quite dangerous. And that's a problem because, when you're trying to evolve life, when you're trying to build these large chains, the fact that UV can come down and like break your DNA chains is bad, we think. But there may be other kinds of life for which this kind of radiation isn't a problem. And maybe, even is a benefit where they take advantage of this, high energy radiation in some way. So Kepler 186f is orbiting one of these M dwarfs, which probably put out heaps and heaps and heaps of X-ray and UV and might have sterilized this planet. Now, do we have any fictional examples of rocky planets in the habitable zone of M dwarfs? We do. This is Superman's homeworld. So the whole point of Superman's powers is that, so he was born on a planet orbiting a red dwarf, an M star, and then he got sent to Earth when his civilization was breaking down. And the fact that the sun's radiation is so different from his home star's radiation is where he gets his powers. He gets his powers because of the sun's radiation being different. So we actually have examples of this in sci-fi as well, planets orbiting M dwarfs. So when we think about what might be habitable, we're not sure if something like Kepler 186f is habitable. Either you're going to die, you're going to get completely irradiated and sterilized by all the high energy radiation, or you're going to get superpowers, in which case, great. But we don't know yet what the answer is. The last one I want to talk about is Kepler 452b. Now, Kepler 452b is pretty close on several of the criteria. It's a little big. It's about 1.5 to 1.6 times the radius of the Earth, which means we're not sure if it's rocky. It's probably right on the bubble of how big something can be and still be rocky. Now, it is orbiting a star like the sun, which is good. And it is orbiting the right distance, the right temperature. It's actually, very similar to Earth's orbit, 370 days or so. So that's all good. It might be too big, but it might be rocky. But it's the right temperature, it's the right kind of star. The problem with Kepler 452b is that it might not be there. When we look at the Kepler data, we see the signature of this planet. And unfortunately, there's a noise signature in the data due to the temperature of the spacecraft actually changing as the spacecraft orbited the sun as well, that looks just like this. So it's very difficult to tell whether the signature of this planet in the data is real or if it's another one of these noise signatures that's what we call a false positive. We think it's a planet, but it might not be there. So, sit a bunch of scientists down and ask them if they think Kepler 452b is real, and you're going to get about a 50-50 answer. It's a coin toss. So, if Earth's civilization breaks down and we need to go somewhere, this might still be our best shot, but it's a coin toss. We might get in our spaceships and go there and then get there and open the door and there's nothing. It was noise all along. So that would be a bummer. But this is basically as close as we got. In terms of science fiction, obviously, as I said with Doctor Who, we're obsessed with Earth-like worlds. So Earth-like worlds are everywhere. So the ones that I like to compare Kepler 452b to are, for instance, Beta Z, another Star Trek planet. Caprica is another one from Battlestar Galactica, which was very Earth-like, blue skies, nice green trees, waters, oceans. So those are the Kepler 452 analogs, the very Earth-like fictional planets. But we still haven't truly found a planet that we're confident is Earth-like, that is a rocky planet around a star like the sun of the right temperature. That's still kind of the holy grail of searching for exoplanets, is finding a true Earth twin. And there's a lot of different astronomers who are on the case, including me, trying to find a true Earth twin. But in the meantime, we found 4,500 of these worlds around other stars. And I want to take a little bit of time to just show you some of the other cool things that we found. Okay, so hopefully you recognize this scene. This is one of the classic. We're going to jump franchises one more time. We're going to go to Star Wars. So this is Tatooine. This is Luke Skywalker's homeworld. And this is this classic binary sunset. So remember I said most stars are actually in binaries. You see two stars together. So this is George Lucas's vision in the early 70s of a binary sunset, of a world orbiting two stars. And that's, as I said earlier, with Kepler 47, we were actually able to find this. And in particular, this is Kepler 16. This is a planet orbiting two stars. It was the very first circumbinary. We call them circumbinary because they go around a binary star. This is the first circumbinary system we ever found. And the reason I particularly love this one is because he even got the colors right. It's a yellow star and a red star. And that's exactly what Kepler 16b is orbiting. He didn't get the sizes right, but again, this was before we'd even found any exoplanets. This was 20 years before we actually had definitive evidence of planets orbiting other stars. And people are already coming up with these very, very cool imaginative ideas. So this is Kepler 16. This is the most distant planet we've ever found. Again, it's an artist's impression. And it's got a very, very long and terrible name. I'm sorry. It's something like Ogle 2018 BLG 0491LB. Really sorry. But it's right towards the center of our galaxy. So if you can picture our galaxy is a spiral galaxy. And our sun is actually just out in the burbs in one of the spiral arms, pretty far away from the middle. But one of the ways that we use to find planets is basically to look towards the dead center of the galaxy, where there's billions of stars all crowded together, and basically see if we see planets going in between us and the center of the galaxy. This is called microlensing. And this one, the furthest away we found is 26,000 light years away. So it's 90% of the way towards the center of the galaxy. That's really interesting because what is it like in the center of the galaxy in terms of radiation, in terms of magnetic fields, in terms of how close all of the other stars are? Like, what do planets experience near the center of the galaxy? And the reason I like this one is the analogy here. We're going to skip franchises again to the Marvel universe, to the MCU. Vormir. So Vormir is the planet, of course, with Red Skull and the Soul Stone, and it's called the center of celestial existence. Which, if you think about our galaxy, going towards the center of the galaxy is the center of celestial existence. So this is the planet that we have found that's most like Vormir. Okay. Recently, there's been excitement about Frank Herbert's series Dune. There's a movie that's just come out, which everyone's very excited about. Have we found something like Dune, also known as Arrakis? So in the story, in Frank Herbert's story, the planet is orbiting Canopus, which is a bright star in our sky. We haven't actually found any planets orbiting Canopus yet. Canopus, though, is a red giant, much later stage in its life than our sun, much bigger and much redder. So you might have heard that in about 5 billion years, our sun will expand, will start its red giant phase, and it will expand and come out to basically the distance of Earth. Mercury and Venus are lost entirely. Earth, we're not sure actually whether it'll get lost or if it'll get pushed out a bit. Certainly it can't stay where it is. But the sun is going to go through its own red giant phase. And we have actually found planets orbiting red giants. And now we've even found planets orbiting white dwarfs, which is the next stage after red giants. After you've puffed off all your outer layers of your sun and you've become hopefully a beautiful planetary nebula, what's left in the middle is just a big chunk of cooling carbon and oxygen, which is just going to radiate forever until the heat death of the universe. And we have actually found planets orbiting those stellar remnants. The reason that's interesting is because A, we didn't know whether planets could survive this red giant phase. Now we know that they can. And B, it means that, all is not lost for our solar system once our sun turns into a red giant and then a white dwarf. Some of the planets might still survive, especially the outer planets. And, we have moons around those outer planets, and some of those moons are rocky, and some of them might even be potentially habitable at that point as the sun expands and the temperature differential in the solar system changes. Like Titan has methane oceans. We've got liquid on the surface there. Let's see what that looks like. So all of this is evidence that our future is not necessarily that, the clock is ticking and in 5 billion years, the Earth is done. Hopefully we've invented interstellar travel by then because there's nowhere to go. The solar system might actually survive, and that's good to know. Something that we have found that is really cool are very, very compact systems of lots of planets packed in really tightly. So this is a schematic of a system known as Trappist I. Trappist I is basically as small as a star can get and still be a star. It's about 8% the mass of the sun. So it's basically just big enough for hydrogen to be fusing in the middle and to be radiating out. And it has 7 rocky planets around it. And those planets are all interior to the orbit of Mercury, of where Mercury would be. So in our solar system, Mercury has an orbit of about 88 days. These planets are all within 20 or 30 days. 7 planets all packed in really tightly. This is another example, KT-138, which actually has 6 planets within periods of 40 days. And this one's very cool because all of the planets are in resonance with each other. Now, when I say they're in resonance, what do I mean? We see resonances in our solar system as well. And resonances are basically when the periods of the objects are related to each other in a very simple way. So the moons of Jupiter, for instance, the 4 Galilean moons, 3 of them are in resonance. So for every 4 times the interior one goes around Io, the next one goes around twice. And for every 2 times that one goes around, the next one goes around once. So they're in a 4:2:1 resonance. It's like clockwork. They're kind of locked in this resonance. And that's how they stay so close and compact together. And for instance, another resonance in our solar system is that Pluto and Neptune are in a 3:2 resonance. For every 3 times Neptune goes around, Pluto goes around twice. And basically these resonances keep everything stable. They keep everything like clockwork, and they tug on each other in a really reliable, repeatable way. And we think that's how these really compact systems of many planets packed in really tightly to their star happen, because of these resonances, because they basically lock them in lockstep together. K2138 is really nice because the planets are all in a 3:2 resonance chain. So for every 3 times this one goes around, the next one goes around twice. For every 3 times that one goes around, the next one goes around twice, and all the way out. The reason that is cool is because the 3:2 resonance in music is the perfect 5th interval. So if you've done any like Western music theory, in the tonic chord, or the first 2 notes of Twinkle Twinkle, it's the perfect 5th, G to C. It's this tonic chord in Western music theory. So it sounds really nice. So what you can do with this system, and what Matt Russo at System Sounds did, is turn it into music. So I'm going to start this video. And what you're going to hear is some music. And basically every time a planet passes in front of its star, it's going to make a note. The faster the planet is going, the higher the note. The slower the planet is going, the lower the note. But the reason it actually sounds pretty and like music is because all the planets are in resonance. So they're all in these perfect 5th intervals from each other. So we'll just take a moment of Zen towards the end of the talk and listen to this. The other really, really, really fun thing about K2138 is that it was found by people like you. It was found by citizen scientists sitting at home, looking at the Kepler data and trying to help us find interesting planets. And there are ongoing citizen science projects to do this. There are heaps of opportunities to look at planet data and help us find brand new planets. So if you're interested at all, especially while, a lot of us are still kind of spending more time at home and still on Zoom a lot, if you're interested in spending some time helping us find planets, you can go to planethunters.org. All the Kepler data are done and have actually been looked at. But since Kepler actually finished in 2018, NASA launched a brand new planet hunting telescope called TESS. So this is the NASA TESS mission. So where Kepler was a big 1-meter telescope that basically stared at one patch of sky for a long time looking for planets like Earth, TESS is 4 10-centimeter cameras. I bet a bunch of you actually have like bigger lenses on your nice fancy cameras at home. 10-centimeter cameras, 4 inches, 4 of them doing an all sky survey. So TESS is looking at every star in the sky, trying to find planets. The cool thing about that is that TESS will find the nearest planets to us. So all of our nearby stars, will scan them all for planets. And those will be the planets that we study for the next 100 years. With our next generation of NASA telescopes, like the James Webb Telescope, which will launch hopefully in December, the Nancy Grace Roman Telescope, which is going to launch in a few years, the ESA Aerial Telescope, which is going to get launched in the back half of the decade. There are lots and lots and lots of opportunities for us to study these planets in more detail. But the bigger they are and the brighter they are and the closer they are, the better we can study them. And that's what TESS is going to do. TESS is going to find all of our nearest, brightest neighbors. Close enough, hopefully, that, it's like borrow a cup of sugar sort of neighbors. The very closest star to us, I'll end with this very cool fact. The very closest star to us, Proxima Centauri, has a rocky planet around it, and we think it's in the habitable zone. That's very cool. Proxima Centauri is an M dwarf, so there's that whole caveat about the radiation, but we've been searching for planets for thousands of years and thinking about them and pondering and imagining and coming up with the coolest things we can come up with. Our very nearest star, that's 3.8 light years away, has a rocky planet around it. That's so cool. The galaxy is full of rocky planets. And I hope that this kind of information goes and sparks more science fiction and more possibilities. It's so cool that, we thought about it for so long and it turns out that it's all true, right? That there are all these planets and they are so different. And some of them are even more interesting than we imagined. And they're everywhere. So I really hope that you go away from this having your mind view expanded of exoplanets and thinking about all of the next generation of interesting things we could find. So thank you very much.
Thank you so much, Dr. Christiansen. You said you catalog the exoplanets, but you don't get to name them. Who does get to name them and how do they do it?
That's a really good question. So planets are named by the team that discovers them. And you would think that that would give them a lot of freedom, but actually they're pretty well constrained by the International Astronomical Union, the IAU. The same people that demoted Pluto quite famously in 2006 have set a bunch of rules about what you can call things. So basically, if the star that the planet is found around already has a pretty popular name, it's in one of these big catalogs, then you take the name of the star, so HD 209458 is the first one that got found, and then you add a little b, just the little letter b. So the star is HD 209458 and the planet is HD 209458 little b. We use a little b because when you use capital letters, you mean stars. So for instance, I talked about the fact that we knew of stars in binary systems and we know of them in triple systems, like 40 Eridani is a triple star system. So capital A is the primary star, capital B is a second star, capital C is a third star. So we preserve that for exoplanets. So capital A is the star, little b is the first planet, little c is the second planet, little d is the third planet. So if the star has a name, it's named after the star. If the star doesn't already have a popular catalog name, then it's named after the mission that found it. So Kepler 47 was the 47th planetary system found by Kepler. Kepler 67 was the 67th. And K2 138, which I mentioned towards the end. So when Kepler had basically a second life as a second mission called K2. And then there's a bunch from the ground like HAT 12 and WASP 53 and TRACE 2 and stuff. So people have a little bit of discretion to come up with what their mission name is. So for instance, one of the very recent ones that we just put in is called Coconuts 2B, because they came up with the acronym Coconuts to describe their survey. Another recent one we put in was called Gotham 2B because the survey was called Gotham. So there's some discretion there, but there are pretty strict rules. You have to get a bunch of people to sign off on them.
How will all of the knowledge we have about exoplanets now impact science fiction? Does our concrete data impact what we can imagine?
I really think it can, and I really think it does. So one of the most interesting things I got to do during the pandemic was assemble a panel of science fiction writers to talk about how they are influenced by real science discoveries. And a lot of the discussion was about, how long do you stick with the real science in your story and where do you deviate to make it interesting, right? Like, where does it become science fiction? And so the fact that we found this like dizzying array of types of exoplanets around different kinds of stars, in different kinds of environments, in different kinds of configurations, I think all of that just opens up more ideas. Like, before you could have written a story about a planet around a white dwarf and, people would be like, okay, maybe. And now we know that there are planets around white dwarfs. It's like, yeah, legit. Like, I don't even have to suspend my disbelief. I know that that's real. There are planets around white dwarfs. So in terms of that like distance you can go where you're still on the real science and you haven't dipped your toe into science fiction yet, we're just making that bigger, right? So that you can stay with concrete science further and further and then add your element of imagination. So I think we're opening the landscape more for more ideas and also, keeping it tied to the real discoveries.
It feels strange that growing up, we only learned about the 8 or 9 planets in our solar system. And now we know there are more than 4,500 planets. How can we possibly learn about space when it is this immense?
The really interesting thing about hunting for planets is how little of the entirety of space we've looked at to find 4,500. So if you think about the size of our galaxy is 100,000 light years from side to side, cribbing heavily from Monty Python's Galaxy song here. And we're out here, in the burbs, far away from the middle of the galaxy. we've searched like this much of our galaxy. If this is the whole galaxy, we've done like this much, and a little line of planets towards the center of the galaxy using microlensing. So this 4,500 is literally just our solar neighborhood. This is all the people around us. There's an entire galaxy, let alone the fact that there are billions of other galaxies. So this exoplanet hunt that we've really only just started in the last 2 decades is just scratching the surface. And we're really excited about upcoming missions that will push this boundary further and start to ask questions like, are planets different in other parts of the galaxy? Are planets different in other galaxies? You know, there's real interesting differences there that might manifest as planets. Like stars are different. Does that mean the planets they make are different? So yes, we have barely scratched the entirety of space yet.
I heard that a giant exoplanet was found just this month, almost as big as Jupiter. What does it mean to find one so large? Or are they all that big? How big are most exoplanets?
We find lots of Jupiter-sized planets because they're actually the easiest to find. They're the biggest, they have the biggest effect on their stars. And most of the time, what we're doing is looking at the star and looking for a change in the star that's induced by the planet. It's very hard to see planets themselves because they're much smaller and fainter than their stars. But actually, most of the planets we found, and we think the most common kind of planet, is smaller than Neptune and bigger than Earth. So in our solar system, there's nothing in that size range. We have a bunch of rocks that are Earth size and smaller, and then a bunch of giants that are Neptune size and up. But most of the planets that we found are actually in between the size of Earth and Neptune. So we call them super Earths or mini Neptunes or sub Neptunes. We haven't really settled on a nomenclature yet. And that's really interesting because we don't know if that kind of planet is habitable. Like once you get too much bigger than the Earth, it changes the surface gravity, changes the pressure in your atmosphere, it changes what your atmosphere is made of. So we have found thousands of these planets and we don't know whether they're habitable, but that's the most common size, is bigger than Earth, but smaller than Neptune.
Can you tell us about the James Webb Space Telescope? How will it impact your work and the search for exoplanets?
In December 2021, hopefully, the James Webb Space Telescope will launch. It's a 6.5-meter telescope that we're going to send out into space. Thousands of things have to go right for it to work. So astronomers around the world are terrified right now of what will happen. But the exciting thing about Webb is that with this huge telescope in space and these really exquisite instruments, we're hoping to peer into the atmospheres of these planets. So most of the 4,500 planets that we found, we don't really know anything about them except a rough size. Like we have an idea of their size. But that's so little information, given that, for instance, in our solar system, Venus and Earth are the same size, but they're totally different planets, right? And then Uranus and Neptune are the same size. They're very different. So one of the things we'd like to do is to get more information. So what James Webb will do is it'll allow us to look into the atmospheres and look for things like carbon and oxygen and methane and water, and start to really classify and say, okay, this is a rocky planet that has clouds and water. This is a rocky planet that just has deserts and nothing, like it's just exposed, like the moon, there's no atmosphere. So Webb is really going to help us learn so much more in such exquisite detail about these planets that we haven't known before. And that's why we're all really excited, because it's genuinely going to open up a new vista of understanding planets that hasn't been accessible till now.
What would it be like for you to find evidence of life on an exoplanet? And what is NASA hoping to discover from exoplanets other than life? Oceans?
Okay, 2 parts to that question. What would it be like to discover life? That's such an interesting question because we don't really know. We can think about what it would be like, but everybody's everyday life would probably be the same, right? You'd get up, you'd drink your tea, you'd go to work, you'd just know that there was life somewhere else. So that's really interesting. Like, how would it change your thoughts about your place in the galaxy and in the universe? How would your outlook change if you knew that there was life out there? Would it change anything about your behavior or your thoughts about the world? And I think the answer is different for everyone, right? Everyone has their own ways that would impact them. But it's such an interesting thing to think about. Like right now, if you found out there was, let's just say, simple microbial life on another planet, what would that change? I mean, for me, even knowing of one other example of life would basically just explode the universe with the possibility of life. Because right now, we only know of one planet with life. That's us. We're the only place we've seen it. We don't see it elsewhere in the solar system yet. we haven't seen it around us in nearby stars yet. And there's something called the Fermi paradox. The Fermi paradox basically says, the galaxy's 13 billion years old. Our sun is 5 billion years old. So there were 8 billion years before our sun was even born for other civilizations in the galaxy to, evolve, become intelligent, develop interstellar travel around, colonize the galaxy. Basically, if anybody could do it, if anybody could come up with interstellar travel and colonize the galaxy, it should have been done by now. And it hasn't. We don't see anything. So does that mean that there's nothing, that there's no life? Does that mean that there is life, but it hasn't worked out how to transcend these very real fundamental laws of physics, travel, speed of light? Does it mean that, there are other solutions, like maybe we're in like a galactic zoo where, they're, whole first contact thing, they're waiting for us to get to a certain point and then they'll contact us. We still feel like we probably should have seen something. Is it like the 3-body problem, like Cixin Liu's trilogy, where everybody's just too afraid to like make their presence known because then they'll get, attacked by someone else? It's so interesting to think about. What would it mean if you heard of life on another planet? I think only you can answer that for yourself. But for me, it would mean that there's probably life everywhere. If life can happen in 2 places, then life can happen any place. So that would be really exciting for me. Okay, the second half of the question, what else is NASA looking for in terms of exoplanets? Life is obviously like the holy grail. Like, are we alone is a fundamental question that has plagued humanity for thousands of years. That's why you have things like religion, right? Because we want to know the answer to the question, are we alone? So in terms of what else NASA is looking for, NASA has a bunch of science questions that we'd like to answer, like how does life happen? And, how do planets happen? And why do different kinds of planets happen? And how do different stars make different kinds of planets? There's a whole bunch of like the science underneath that, the physics of like, what are the physical mechanisms that sculpt planets? And what does that mean? That's the where do we come from in the, solar system sense, how did Earth happen? Why do we have oceans? Do they come from comets? Is Jupiter good or bad for life on Earth? Does Jupiter have a net positive effect or a net negative effect? Just the fact that Jupiter exists. There's a whole bunch of really interesting questions just about, the history of Earth and what that might mean that NASA's trying to answer. And also, there's this saying that this is the generation that was born too late to explore Earth, but too soon to explore space. And I don't feel like that at all, because I get to explore space. I get to find new worlds around other stars. So one of the things that a lot of the people at NASA are trying to do is just discover things, just to find new things, like the sense of exploration. The fact that I get to go to the telescope and be like, that star, I'm going to look for a planet around that star. And then there's a planet and you're like, yes, publish. That's, the thrill of why I do it, right? I get to discover things. So the people at NASA are very driven by curiosity and exploration and science. And NASA as a whole is driven by these big fundamental science questions of how does all of this happen and how do we understand it? And, we are the universe's way of knowing itself, as Carl Sagan says. So NASA is humanity's way of trying to understand the universe.
If you found an exoplanet that supports life, could we get there?
Something that's really fun, but also depressing about space is that it's really big. It's really, really whoppingly very large. So even the fact that our very closest star, Proxima Centauri, 3.8 light years away, has a planet around it, doesn't mean much for us right now here in 2021 on Earth. We have no way of getting there. People are developing technologies like light sail technology, where you throw up a giant thin foil and the radiation pressure of the sun pushes you. So people are thinking about technologies, but right now for us, there's no way that we could go to any of the nearby planets. One of the fun ideas that people think about is generation ships, where, let's assume you can't break the laws of physics and you can't go faster than the speed of light. Lots of the planets that I've talked about already are thousands of light years away. So that's still thousands of years, even if you were traveling at the speed of light. So something you can think about is generation ships, where, you live and die on a spacecraft and eventually your descendants get to where you're going. So that's something that doesn't break any laws of physics. We just haven't worked out the technology yet for, how would you sustain, how would you repair things? How would you, keep all of the essential nutrients and amino acids and everything you need for thousands of years. But that doesn't break any laws of physics. So in the absence of someone discovering faster than light travel, basically breaking the laws of physics, there's no way for us to get there. So at the moment, these are all really, really cool discoveries that remain very abstract. But that doesn't mean that I don't think in 10,000 years or 100,000 years or a billion years, we might not work something out. But that right now for us on Earth, the fact that we have found cool planets nearby isn't something, it's not like an escape hatch. It's not like we can be like, all right, well, climate change made Earth too bad. Let's go to this nearby habitable planet. That's not a solution for us. We've got a long way to go before we're going to any of these planets.
Thank you so much, Dr. Christiansen. It's been a pleasure to have you.